Hello everybody and welcome to my fifth lecture on network systems. Great pleasure to have you. Thank you for watching these videos. Today, chapter 5 deals with the analysis of discrete-time averaging systems. So we had discussed several examples of this in the first lecture. And then in chapter 2, 3, and 4, we prepared a body of material, the Perron-Frobenius theorem with the matrix power theorem in chapter 2, and then the language of strong connectivity, globally reachable nodes, and so on and so forth, and even condensation of digraphs in chapter 3. In chapter 4, we discussed how to connect adjacency matrices and their powers to the connectivity properties given in chapter 3. So now I'm ready to give you an outline of this chapter, and it works like this. So let me remind you that in chapter 2 we saw the following. We saw that if A is primitive and rho stochastic, because we are dealing with averaging systems now, this implies that A to the K converges to 1n W transpose, where 1n is the right dominant eigenvector of the eigenvalue 1. So remember, rho stochastic means that A1n is equal to 1n. We also know that A is non-negative, right? And then because A has an eigenvalue equal to 1, it has, of course, a right eigenvector, but it must also have a left eigenvector, W. And that left eigenvector has exactly this property, right? And in order for the theorem to hold, this is the matrix power theorem, I need the normalization 1n transpose W equal to 1. So in other words, W is a vector of convex combination coefficients. It's a vector of percentages. And so what that means is that in terms of our averaging system, if the matrix A is primitive, now we know that X of K, when K goes to infinity, converges to W transpose X at 0 times 1n. And this is asymptotic consensus. This is asymptotic consensus. So we know that the property of being primitive is really important, right? It's the key property. So that was chapter 2. In chapter 4, we've seen that A primitive, if and only if the directed weighted graph associated to A is strongly connected and aperiodic. So that's perfect. So now we know graph theoretic condition. We know that if G has some connectivity properties and some properties in its loops, then A is primitive. And if A is primitive, we know that this limit holds, and therefore we get asymptotic consensus. This is great. However, this body of reasoning has one slight weakness, which is that this arrow, this implication, only goes from left to right. And what I want to do today, and that's one of the main topics of this chapter, is to ask myself the question, suppose I really wanted this property to hold, then what is this property if and only if with? What is the property here that I don't know that tells you when that holds? All right, so all of this that I just discussed up to here is review, and it's meant to set up the fact that we are going to have in chapter 5, we're going to have a main theorem, right? A first main theorem, giving you necessary and sufficient conditions for AK to converge to a vector of the form of this form, right? That's the main theorem. And we're going to I'll give you if and only if conditions, right? We're going to have an understanding of that. Additionally, another weakness of this line of thinking, right? Well, not a weakness, but another part that is incomplete is the following. If G is strongly connected in a periodic or whatever other property, then I obtain asymptotic consensus. Marvelous. But I am also interested in the cases where, again, we will study a second theorem. So maybe we can call this the first theorem. The second theorem will be about, what about the case where we have asymptotic disagreement? People also call this dissensus. So this was consensus and now asymptotic dissensus or disagreement. So in other words, maybe you're in a situation where some individuals, so a subgroup of individuals reaches a certain final value, maybe a different group, or in any case, individuals, the opinions of individuals do not become uniform and all equal to each other. Perhaps they reach a range of values, right? Again, in the consensus manner, the value to which the final opinion of everybody converges to is W transpose X at 0. W is a vector of convex combination coefficients, so this is a convex combination of the initial opinions. So even in the dissensus, you will see that final opinions are convex combination of the initial opinions, but they're not all equal to each other. Now, I will also, okay, so the proof of all of these two theorems is ultimately connected with the Jordan normal form. So if you look at the proof in detail and you go through it carefully, you will see that to prove convergence, we write the Jordan normal form, we take the powers of the Jordan blocks, and we get to our conclusions. And that's the way we proved this result, for example, and that which is the one we were going to use. However, I will then show you in a third, let's say third section. I'm going to say section because I'll have multiple results. I'll show you an alternative approach whereby I will start to talk to you about something called Lyapunov functions. And in particular, and I will talk to you about basically contraction factors, which are referred to in this literature as ergodicity coefficients. So these ergodicity coefficients, it's an unusual term. We haven't discussed. I'll get to it. I'll get to it later. And then I will just briefly show you in a fourth section. In the fourth section I will show you a little bit of just two simple design algorithms. What is a design algorithm? I mean to say, I give you a graph, just a topology, meaning to say just the edges, and I ask you to design the weights for the edges. We will design the weights in two different ways using something called the equal neighbor algorithm and the Metropolis-Hastings algorithm, and we will see what those design lead to. And then there are some appendices that I may just quickly look at, but I will not cover in detail. All right, I am now able to begin the chapter, and as discussed in the outline, I am going to provide you with theorems that describe when does the system reach asymptotic consensus. By system, I mean to say the dynamics xk plus 1 equal to axk, whereby A is a row stochastic matrix. Now, let me just review quickly things that we've seen and just put them together. Essentially, at the beginning, I'm just going to put together concepts that we've already seen. So imagine we look at this picture on the left here. This is an image of a graph of a weighted directed graph we work with in chapter 1. This is the corresponding row stochastic matrix. You look at the graph, clearly it's strongly connected. Clearly it has self loops of length 1, therefore it's aperiodic. Clearly the matrix A wireless sensor network, that's the name I gave to that matrix. Clearly the matrix A WSN is primitive. In fact, we even saw it. Therefore everything works. Clearly we can use the matrix power theorem and we get this limit which we wanted. We can also compute W. It's the first row of T inverse. We did that in chapter 2. And W had this very neat expression, 1/6, 1/3, 1/4, 1/4. And we get consensus. No need to introduce any new theorem. This is just basically putting together everything we've achieved. One of the questions that we came up with in chapter 2 was, suppose I want to design an algorithm whereby the final value, the final consensus value, is equal to the exact average of the opinions of the nodes at time 0. Do I achieve that with this particular design in this figure 5.2? Do I achieve it or not? And the answer is no, I don't achieve that because W is 1/6, 1/3, 1/4, 1/4. Notice that if you come back to this picture, let me maybe add the numbers here. So this is 1/6, 1/3, 1/4, 1/4, and clearly these numbers sum to 100%, sum to 1. Notice that the node 2 is connected to all the other node, has a larger weight, has a larger weight than the nodes 3 and 4. 3 and 4 have the same number of neighbors, and they have, the weight 1/4, which is in the middle between the larger number 1/3 and the smaller number 1/6. And 1/6 has a smaller number of neighbors. Node 1 has a smaller number of neighbors, and its weight in the final combination coefficient is 1/6, which is smaller. This is not by chance, and we will understand this when we do the equal neighbor model in a later section. But the point is that for sure the vector W being equal to 1/6, 1/3, 1/4, 1/4, this vector is clearly different from the vector 1 over n, 1n. Well, in this case it would be 1 over 4, 1/4, which would be basically 1/4, 1/4, 1/4, 1/4, right? That would be the vector that would give us average consensus. How do we achieve average consensus? Here comes the second example. In chapter 1 there was in an appendix, I don't know if you had a chance to read it, I remember skipping it in the video, but there is a robotic pursuit problem. It's a cute problem. It's a very nice little problem, and it has to do with a topology of a directed graph, which is a ring topology, and it's fully people say it's fully invariant under rotation. So every node has exactly the same self loop of weight 1/2. And an edge going to the immediately next clockwise neighbor with weight 1/2. And so again, you look at this picture and you realize easily, again, this is strongly connected and aperiodic. There is a loop of length 6, there is a loop, but there are loops of length 1. There is a simple cycle of length 6, but there is also a simple cycle of length 1, which are the self loops. Now you can write down the corresponding row stochastic matrix, and you can observe that, well, if you wanted to, you could check it. It is easy to even just by hand compute the powers, and you will see it's primitive. But you don't even need to do that, because the theorem about primitivity tells you that if it's row stochastic, if the graph is if the graph is strongly connected and aperiodic, then the corresponding matrix has to be primitive. So now we know that we converge to consensus, but additionally, it turns out that this particular matrix, A pursue, if you look at it, you can sum rows, and every row you sum gives you row sum equal to 1, but it turns out that also the columns sum to 1. Also the columns sum to 1. And so what that means is that now I have a doubly stochastic matrix. The left dominant eigenvector is the vector of 1s. And so it turns out that we now reach average consensus. So average consensus is reached when, in the second example, on top of all the properties in the first example, we also have column stochasticity of the matrix A. Here's a third example that is a bit of a stimulating example. So suppose I have a problem where, I'll start with the equation, which is simpler, where some individuals, let's say just two nodes, two individuals. The second individual is willing to average its opinion with the opinion of individual one. But individual one is fully self-absorbed. Individual one does not change at all its opinion. So then a very easy outcome of this dynamics is that x1k, when k goes to infinity, converges to x1 at time 0. Basically, it never changes, really. And then what happens to x2? x2k is repeatedly executing averages between its current value and the value x1 at time 0, repeatedly for an infinite number of times. It's like that story of the animal, of the rabbit, that takes, is it ever going to step a step equal to 1? You take half a step to the distance at each time, and because you take an infinite number of steps, it turns out that you will actually converge to x1 at time 0. So in other words here, this is asymptotic consensus. But it is not true that the corresponding graph is strongly connected, because this graph is depicted by a picture where node 1 looks only at itself and node 2 looks at itself and looks at node 1. Such a graph has a node 1 from where you cannot go to node 2. So this is not strongly connected. It does have the property, however, that node 1 is globally reachable. And now you start to see that something interesting is happening here. So here I have a picture of a randomly generated row stochastic matrix. It's a pixel picture of the matrix, of a row stochastic matrix. Nothing fancy. I then drew the associated digraph. And then as you look at it, you can perform the condensation partition. What happens here? Pick any of these darker gray nodes and follow directions, and you will see that from any node you can go to every other node. I have drawn with my pen various directed paths that follow, are consistent with the directions of the edges. And so what this means is that if I were to draw this line like that, you can think of that as a cut of the graph. All of the nodes inside that closed curve constitute a strongly connected subgraph. And moreover, I cannot add this node here on the left of this other node, this node here on the right, or this node here on the left, because if I do that, my subgraph becomes not strongly connected. So what I'm trying to say here is that these nodes enclosed in the surface here, in the closed curve, they form a strongly connected component. And they are globally reachable because also from the other two nodes, the one on the right here and the one on the left, there exist directed paths to any node inside the strongly connected component. So in other words, this, how would we call this? This is a strongly connected component of globally reachable nodes. I apologize for the two abbreviations one after the other, but It's a strongly connected subgraph. It's a component. It cannot be grown any longer. And those nodes are globally reachable in the graph. I will also notice that in this particular picture, if you count the lengths of simple paths, while exist no self-loops, still there are loops of length 2. For example, here, this is a loop of length 2, and then this is a directed cycle of length 3. And so 2 and 3 are co-prime. So this particular example also happens to satisfy the following property. The strongly connected component of globally reachable nodes is also aperiodic, and that's very useful. Now, it's important to spend a second on the picture on the right. So this is illustrating to you. What is illustrating? The eigenvalue is at 1. There's an eigenvalue at 1, and all of the others are inside. And so this is, let me remind you, there was a property in chapter 2 of something called semi-convergence, right? The property is that AK will converge to something, I don't know yet what that is, and that property holds whenever the eigenvalue 1 is semi-simple and all the other eigenvalues are strictly inside the unit disk, and this is satisfied here. This is satisfied here. Perfect. And this is not a strongly connected matrix. Okay, now we're ready. So here is the first main theorem of this chapter, certainly of this section. Let me start with the easy conclusions. The easy conclusions are that I am interested in working with the case where I achieve consensus, and W in the consensus value is a left dominant eigenvector of the matrix. But I want to give the weakest possible conditions. We already saw in the outline, we already saw that if the graph is strongly connected and aperiodic, then I achieve consensus. But what we want to do is we want to do the if and only if here, right? We want to reach a stronger characterization. So what is the property that I need to ask for? And these are given in these three equivalent conditions, A1, A2, A3. A1, A2, A3. So what are these conditions? So A1 is, and these conditions are equivalent. I want to set myself in the setting where the eigenvalue 1 is simple and all other eigenvalues are strictly dominated in magnitude. I want to set myself in the case where, alternatively, A2 is that A is semi-convergent and the limit is a rank 1 matrix where, again, W is the left dominant eigenvector of A. It's normalized to have row sum equal to 1. However, now my matrix is not necessarily irreducible, which means that the entries of W are not necessarily all positive. They are non-negative. Clearly, at least one entry has to be positive because otherwise the row sum of W cannot be 1. And here is the key insight. These two conditions A1, A2 are if and only if with the third condition here, and the graph theoretic condition, the one that is easy to interpret and then ultimately even to check in an algorithm on a computer in a piece of software, is the following. My graph has to contain a globally reachable node, at least one, perhaps more than one, and the subgraph of globally reachable nodes has to be aperiodic. I will make a comment. If a subgraph of globally reachable nodes has one more property that is not stated here. If two nodes are globally reachable, that also means that from node 1 I can go to 2, and from 2 I can go back to 1. So that means that, and additionally, if a node is not globally reachable, that means I cannot possibly find a path from the node in the globally reachable subgraph to a node outside of the set of globally reachable, because otherwise that node outside would also be globally reachable. And so really what I'm saying here is that the subgraph of globally reachable node, it's actually a strongly connected component, just to clarify. And I need that to be aperiodic, because if I have periodic behavior anywhere, then there will be periodic oscillation in the solution of the averaging system, and I don't Right now I'm not interested in periodicity. I want to show asymptotic convergence to a value. But the key idea, except for this aperiodicity, the second clause, the aperiodicity clause, the key idea is that I achieve consensus if and only if there exist globally reachable nodes, one or more. Now let me go over the consequences again. So if there exists if any of the three conditions A1, A2, A3 holds, they are equivalent, then this class of matrices is not irreducible and certainly not primitive. I want to give it a name, and I will call it indecomposable. So if any of the three conditions A1, A2, A3 holds, then the matrix A is said to be indecomposable, and it has its left dominant eigenvector exists, and it has and it has a special property. The property is that the entry of the eigenvector which are positive are precisely those corresponding to nodes that are globally reachable. So that's very interesting. So in other words, if I have that graph a few seconds ago I showed, node 2, node 1, node 2 is not globally reachable, node 1 is globally reachable. The left dominant eigenvector of the corresponding row stochastic matrix is going to have to be of the form 1, 0. It is 0 because 2 is not globally reachable. It is non-zero in the first entry because 1 is globally reachable, and it is precisely equal to 1, the first entry of W, because node 1, because we know that 1, 2 transpose W must equal 1. All right. And this W is useful because this is the consensus value to which you converge. And in fact, we saw it in the example 2 slides ago, that for this very simple two-dimensional example, xk was converging to x10 for both entries. So I had basically 1, 1, and I can write that as W transpose x at 0, which multiplies the vector 1, 2. You see, we saw this in the example 2 slides ago. Additionally, and finally, if it were to be the case that A is doubly stochastic, then we would actually get average consensus. And something is missing. It's not missing, but to keep the theorem simple, I could also convince you, I think, that if I have a globally reachable node, the existence of a globally reachable node plus a matrix that is doubly stochastic, these two things imply, what do they imply? The existence of a global reachable node implies, for example, that the graph is weakly connected, and the fact that the degeneracy matrix is doubly stochastic, it means that G is balanced. And in one of the exercises in chapter 3, these two properties are shown to imply that G is strongly connected. So it turns out that asking for A to be doubly stochastic in the setting where you have a global reachable node is equivalent to also asking for G to be strongly connected. So if you are converging to the average value of the initial opinions, it must be possible that from every node you can reach every other node. That's only very reasonable, because it would be impossible, there would be an easy contradiction to imagine that your group of nodes reaches average consensus, which means that even a node J, the final value of node J, contains 1 over n of the value of node I, and that's only possible if there exists a directed path starting at I going all the way to J. Otherwise, the information cannot travel on the directed graph. Perfect. So this is my main first theorem, and this is giving you that promised if and only if condition. Now, right now you know that you have this, and let me erase to give you this additional interpretation. Let me make it a little bit cleaner. Once again, the if and only if condition is, I want to know when I converge to a rank 1 matrix with being of the form 1nW, where 1n is the right dominant eigenvector. So I have, and that is consensus. I have consensus if and only if there exists a globally reachable node, and together the globally reachable nodes are aperiodic. Now, Before I jump to the second theorem, okay, here's a little example. 3 slides ago I had an example that I randomly generated. This is an example, it's a nice little example from social science. There's something called Cracker Advice Network. I will let you read it. One of the points that we're making in here, that I'm trying to make in this picture, is that some nodes, for example, this dark, so in this picture, the gray level of the nodes is proportional to that. So the gray level is proportional to Wi, which is the entry of the W vector, the left dominant eigenvector. And so this node is very dark. These nodes are completely white. These nodes are not globally reachable. So for these nodes, let's call them J, Wj is equal to 0. They play no role. In the final consensus value, they play no role because they are not globally reachable. All of these other nodes are globally reachable, so they all have non-zero Wi. However, some nodes have larger Wi than others. And that gives you a notion of centrality in the graph. And so this node here that I have highlighted is the most central node. And then in terms of grayscale, you can see that this is that's the second most central, the third most central. And so centrality here means influence. So the final value to which the entire group converges is very much influenced by the nodes with a larger Wi. Let me give you just a tiny bit of intuition for the proof. And the longest thing and the most difficult thing for me here for you is just to remember what A1, A2, A3 were. A3 is G has globally reachable nodes and they're aperiodic. A2 is that A to the K converges to 1n W transpose, and A1 is that, let me see it again, forgive me for, oh yeah, of course, it's the spectral characterization, meaning to say 1 is strictly greater than the magnitude of mu. And so the picture here is there. This is the picture. The picture here is that the eigenvalue at 1 is strictly dominant and simple. Right? So that, let me just show you one more time. Here the statement is that the eigenvalue has to be simple. All right. And I emphasize that because there will be, because if you remember carefully from chapter 2, convergence is allowed, convergence takes place also when the eigenvalue 1 is semi-simple. And so here we're giving if and only if conditions for consensus, not for just semi-convergence. That's going to be the next theorem. All right. So how do I show that A1, A2, A3 are equivalent? Well, the fact that 1 implies 2. No, sorry. Let's write it like let's just emphasize here. It's precisely the matrix power theorem. This is the theorem where I said that if the matrix has the Perron-Frobenius property, the strongest property for primitive matrices, which is to say having a strictly dominant simple eigenvalue, then it converges. So we already did A1 implies A2. That was the old theorem. The second property is really kind of cute and very simple to understand. Why is it true that, the second implication. So I have shown to you that A1 implies A2. I need to show you that A2 implies A3. So that's what I meant. How do I show that, that this implication holds? Why is it true that if I converge to 1n W transpose, then there exists a global reachable node? And what is that global reachable node? Well, here comes a very simple fact. If AK converges to this matrix, 1n W transpose, what is this matrix? Well, we actually saw this, and this matrix contains repeated copies of the vector W transpose as rows. Now, if an entry, because of property A2, we know that there exists one node I such that Wi is greater than 0. So if I come to my matrix, maybe let's make it J for a second. So if I come to my matrix, I know that there exists a J such that that entire column of 1n W transpose is strictly positive. But if this column of one NW transpose is strictly positive, for sufficiently large K, you see AK is converging to this matrix, but then for sufficiently large K, also the jth column of A to the K must be positive for sufficiently large K. And what does that mean? That means if that column is positive, that means now we're using that fundamental lemma in chapter 4. Oh, but this means that, so this was the first implication, here's the second implication, there exists paths from all I to j of that length k, right? Because the entry of the jth column are of the form, the arbitrary entry here is a I, well, I should write better because otherwise it's confusing. I should say a to the k, close the parentheses, it's I, aij. So if this is positive, if the column is positive, it means that aij, a to the k, ij is positive for every I. So there are paths of any length, from any node I to the node j. And so this means that j is globally reachable, right? Very, very simple proof which puts together concepts that we've seen. Perfect. So I have now proved to you that A1 implies A2 and that A2 implies A3. So now I need to quickly give you some intuition for the final proof. How do I know that if A3 holds, then this implies the other two. And here I see that I don't have space. Forgive me. I will put it back here then. Sorry about that. Little silliness. So I am going to now show you that A3 implies the others. Okay. So how do we do that? It's done in essentially three steps. We start with something very simple. Then there is one little key insight, and then there is one final silly calculation that it's a little tricky, but that it's very simple. So now, because the condensation contains a sink, which is the group of connected component of globally reachable nodes, it turns out that you can write the adjacency matrix in this lower triangular form. And therefore, you can write the dynamics of the averaging algorithm after a possible permutation of the entries in that form here, in this form 5.3, 5.4. So again, I'm using the fact that exists a globally reachable node. The globally reachable node is the inside. All of the nodes are in the vector x1. And the fact that you have this matrix A to 1, right, intuitively or roughly speaking, this means that there are entries of the form A to 1 strictly positive, just like the two-dimensional example that I have done, right? So the matrix, more specifically in this case, the matrix A to 1 is non-negative and A to 1 is different from 0. Otherwise, the nodes in the sub the node indexed by the index 1 would not be globally reachable, would not be reachable by the nodes in 2. Vice versa, the nodes in 2 are the ones that are not globally reachable, and that's why I have zeros up there. If all nodes are globally reachable, then the graph is strongly connected, and then I'm done, and then the proof is complete. I don't need to worry about anything anymore, because if it's strongly connected, then I can use the old theorems about primitivity and so forth. Now, if you look at this dynamics, okay, so far this was a first simple observation. Here's a second simple observation before I go to the more substantial observation. If you look at this dynamics, A11 has to be row stochastic because the matrix A is row stochastic, and when I do the row sums of A, the first entries are going to be row sums of A11. So A11 is row stochastic, and it corresponds to a strongly connected component, a strongly connected subgraph. Therefore, it's irreducible. I additionally assumed it was aperiodic. So A11 has all of the properties in the world, and so A11 must converge to consensus. A11 works. So the first subdynamics there converges to consensus. And so this is relatively straightforward because the nodes in the subgroup 1, the global reachable nodes, are not even listening to they are evolving in an independent manner. Okay, now, what happens to so this was nice. Now the key question is, and now comes the smart observation that I was referring to, is what happens to the second dynamics, x2? Now, if you look at the second dynamics, x2 of k plus 1 depends upon x2 at time k through the matrix A22. And the other entry, it's an external input. So the dynamics in x2 is affine. It's affine and it's dictated, its state matrix is A22. Now we've seen examples in chapter 1 where I have an affine dynamical system and I want to know if it converges. Well, I really need to show that rho A22 is less than 1. If rho A22 is less than 1, then I know that it is a convergent system, and for any constant, for any input, it will converge to a final constant value. Perfect. So now why do we know that rho A22 is less than 1? And now comes the nice idea. A22, maybe I want to draw a picture here. We are in a situation where I have a group of nodes which are globally reachable, and then I have other nodes that are not globally reachable, but when I do the cut, there for sure is at least one edge going from bottom to top. A22 is the non-negative matrix describing the interaction between the second group of nodes, and A22 multiplied by a vector of ones of an appropriate size is less than equal than 1, because it's at most 1 if these were decoupled, but precisely the existence of these edges ensures, well, at least one edge must exist, which means that at least one row sum of A22 is strictly less than 1. So A22 is row substochastic. It's row substochastic. At least one entry points out. And remember that, let's imagine for a second, for simplicity, there exists only one path. So then there exists one node here. There exists one node here that points to a node in the globally reachable sets. On the other hand, from every other node in the second, here at the bottom, there must exist a directed path to the globally reachable nodes because they are globally reachable. So in other words, from every node, let's say I take this node H, there must exist a directed path to a node L, and then from L I go into the globally reachable nodes. So then I prove that there exists a directed path or walk from any node L that is not globally reachable to the node from any node H that is not globally reachable to the set of globally reachable nodes, right? And in particular to a node that goes into the set. So to cut a long story short, these are precisely the two properties that we used in chapter 4 to establish that my row substochastic matrix A22 is strictly convergent. So that's the key idea of the proof. And now, from now on, the rest is just calculations, which I am going to skip. And I will just mention that there is just one little trick here that has to do with thinking carefully about what does row stochasticity mean. And you get one more algebraic equality that you use. Okay, at this point in time, I will take a little break. Let's do that. All right, perfect. So I'm now ready to cover section 5.2. We saw one nice theorem that gives necessary and sufficient conditions for convergence to consensus. And it has to do with the existence of globally reachable nodes. But two comments. One is, mathematically, if you remember, the convergence for the convergence property, the convergence theorem in chapter 2 said that the matrix has the semi-convergence property, which is to say that a to the k converges to something if and only if the eigenvalue 1 is semi-simple and 1 is strictly greater than the magnitude of mu for all other mu, for all other eigenvalues, and and 1 is an eigenvalue, of course. So what I'm trying to remind you of is that in chapter 2, in the convergence theorem, we are allowed to have semi-simple eigenvalues at 1 to have convergence. We does not need to be simple. Instead, in the theorem that we just saw, the eigenvalue 1 is simple if and only if there exists a global reachable node. So this hints at the possibility of convergence to something, not necessarily consensus, even when even more generally than the theorem we just saw. And in this section, this is a quick section which shows you one such example, and many things come together. It just all works out, of course, as one would expect in linear systems. So I am still converging to something, but it is not consensus. And here's an example, here's another example from social sciences, another data set. This is a monastery data set by Dr. Sampson. It's a classic data set. And here I have drawn a directed graph between 18 nodes, 18 individuals. And in this graph, it just so happens to be the case that what they self-reported as friendship and advised relationships, that there exists a strongly connected component of nodes. There exists another strongly connected components, and there exists some isolated individuals, which you can also think of as strongly connected. And if you think about the condensation associated to this graph, the condensation associated to this graph looks like this. Looks like there are 5 strongly connected components. The first isolated individual points to, points only here. The second one also like that. And that one is like this, right? So hopefully you see what I'm doing. So this isolated individual corresponds to that node. And this node here in the condensation points to both 2 sinks of the condensation. Again, the condensation has 2 sinks because there's no outgoing edge from here, sink 1, or from there, sink 2. And so both sinks appear in the condensation. This is the first example I'll show you of a condensed digraph with 2 sinks. And because there exist 2 sinks in the condensation, in this example, there exists no globally reachable node. There exists no node that can be reached from all others, right? Intuitively, these nodes are the ones that can be reached from almost everybody. However, not everybody, because the nodes that are in that other sink have no way of reaching the nodes in the first sink, right? And vice versa. And so the way you would expect, I'm only going to say this, informally. The theorem says that the following 3 properties are equivalent, and now you allow the eigenvalue 1 to be semi-simple, the matrix is semi-convergent, and the requirement is that each sink of the condensation be aperiodic, because again, if you have a strongly connected graph that is periodic, then what will happen is that information will just travel in a periodic manner, and there will be no convergence to a specific value. And the last thing I'll say, so these are 3 equivalent conditions, and I will, if you're interested, let you read the proof. The proof is very simple, and you just compose together the properties that you have already established. And I will just reason with you for a few seconds about what do you expect the final value to look like. And there are a couple of very simple observations that one should make. Well, this group of 2 individuals is strongly connected, aperiodic. Well, actually, I forgot to draw the self-loops here. Otherwise, that is periodic and it wouldn't converge. But there are also self-loops, so it's periodic. And clearly, it's reaching consensus. These 2 guys don't talk to anybody else, and they reach their own consensus value. How many nodes there are? 18, 2 plus 3 are out. So the 13 individuals who are in this larger strongly connected component don't listen to anybody else, run an averaging algorithm, strongly connected, aperiodic. They reach their consensus value. So now you know that these individuals reach consensus, these individuals reach consensus amongst themselves, but the value to which they both of this subgroup converge is different. They're necessarily not the same, right? Completely arbitrary. Now, what does that mean? These two nodes happen to only listen to one of the two sinks. Therefore, they themselves will converge to the same consensus value to which sink number one converges. Now, the final most interesting case is that of this individual who cognitively gives some weight to the opinion of sink 2 and to the opinion of sink 1, and so it will converge itself to some convex combination half the way between the value of consensus of sink 1 and the value of consensus of sink 2. And all of these statements that I have given to you can be rigorously established. That's what this is saying. Basically saying that if you have a node I and the node belongs to a sink, then it goes to a consensus value. And if not, if it doesn't belong to a sink, it goes to a convex combination of the consensus values of the sink, but the convex combination coefficients are positive if and only if there exists a directed path, a directed walk from node I to the sink P. Perfect. Very neat result. In summary of these two sections, we have reached an ability now to classify the behavior of row stochastic matrices. This is really extending that table from chapter 2 where we classify the row stochastic matrices. And as you remember, we decided that some matrices were irreducible but not primitive, some were primitive, some are primitive and also doubly stochastic. Other matrices which I've introduced today are indecomposable because they're not irreducible, but then it is possible when you take the powers, one of the columns becomes positive, right? Now, this is a Venn diagram. So inside the set of all irreducible matrices, one subset are the ones that are primitive, and then another subset are the ones that are double stochastic and primitive. And the meaning of these arrows is that literally what I'm trying to say here is that this particular block here corresponds precisely to that block and this block. And so here what I'm listing are properties of the directed graph, properties of the row stochastic matrix A, and properties of the averaging algorithm. These are all connected one another. The digraph, A is the adjacency matrix of G, G is the digraph associated to A, and once you have the averaging system, of course, you can extract the matrix A. So these are all in one-to-one correspondence, right? And what I have proved for you so far, it's almost everything that you may want to wonder about this picture, which is to say that we've seen all of it. So we've seen the fact that let's start with the strongest case. And let me clean up so I can do this from scratch. So the matrix is double stochastic and primitive if and only if the algorithm converges to average consensus, if and only if topologically, so the graph is strongly connected, aperiodic, and weight balanced. Here's another case. Instead, if the matrix is primitive but not double stochastic, or another way to put it, the graph is strongly connected and aperiodic but is not weight balanced, then the algorithm converges to consensus, and the consensus depends upon this eigenvector W, and W is positive for all nodes. In some other cases, you may converge to consensus, and the convex combination, the opinions that have a weight in the final value, are the ones that of only some nodes, not all nodes. So the consensus value does not depend on all nodes, depend only on some specific nodes. Well, it turns out that those nodes are in the sink of the condensation. They're globally reachable. The condensation has to be aperiodic. The sink in the condensation, so the strongly connected component of globally reachable node needs to be aperiodic. I know it's a little bit of a mouthful. Or alternatively, the matrix is indecomposable. Now, instead, if you have that, you have multiple aperiodic sink components, this is the very last case, then you do converge to something, but not to consensus. You converge to final values. Each sink converges to a consensus value, and the nodes that are outside the sink converge to convex combinations of the consensus values in the sinks. Now, instead, in the entire right column here, this is to remind you that it is entirely possible that the graph is periodic. And if the graph is periodic, then you have oscillations and there is no convergence. Perfect. So this is fine. And this concludes my discussion of this section. All right. Wonderful. I'm now ready to discuss section 5.3, which is a section on giving alternative proof methods. And these proof methods have to do with the concept called Lyapunov function. And because of that, these are proof methods that are more general than ultimately the linear methods based upon Jordan normal form that I have studied so far. So let me give you a little bit of intuition of how you would go about understanding this convergence to consensus results in a way that is generalizable and does not work only for linear time invariant systems. And because, of course, not all network systems are linear time invariant, right? So we are going to have to understand those as well. And if you had a chance to take a course on stability theory for nonlinear systems, you know that this methodology of Lyapunov function is very general and very powerful. All right, so let me talk to you about, I'll take a first step and then I will give you Lyapunov function. So the first step is the following. So once again, let's go back into the consensus case. So I have an averaging system and I have a row stochastic matrix A, and it's non-negative, so therefore by the Perron-Frobenius there exists a left dominant eigenvector, non-negative, it could have symmetry equal to 0. And I normalize it because it doesn't cost me anything, so I normalize it. So we already have a suspicion that under mild conditions, what will happen is that xk or x at k will converge to W transpose x at 0, 1n, and another way to write that is to write that as and that's the matrix, and that's because a to the k will, under some conditions, converge to an W transpose, right? So this matrix is a rank 1 matrix. It's a very important rank 1 matrix. And I'll use it right now to define something that I call the deflated matrix. So I take A and I subtract from it its limit. So now reason would be that if you subtract the limit from A, then maybe under some conditions it may be true, well, it will turn out to be true, that if you take this limit you get 0. You get the matrix of zeros, right? So we'll come to that in a second, but that's the intuition behind why you do this deflation procedure. And in the same spirit, I can take the vector x and subtract from it the value to which it will converge, which and more specifically, I will subtract the value at time k, which is W transpose xk. And it's actually really the same. Let me make some comments. W transpose k is a convex combination of the entries of xk, and it's easy to see that it is constant in time. So it's easy to see that W transpose X at K, it's equal to W transpose X at 0, and it's equal to any other time. So essentially you're just subtracting from xk its final value, right? Its final value. It's also easy to see that this rank 1 matrix that I'm talking to you about happens to have the property that if you square it, you get back the same matrix. And I will let you work this out on a piece of paper to just see how easy that is. There's also an exercise in the book on this particular matrix. And because it has this property of, the power is equal to itself, people refer to this as a projection matrix. Projection. It's a projection onto a one-dimensional space. Now, the last thing I want to say is I'm calling this deflation. What does deflation mean? Deflation, loosely speaking, means that when I deflate a matrix, I remove the influence of the eigenvalue that I am deflating with respect to. So here, this projection matrix 1n W transpose, these are the right and left eigenvector of the eigenvalue 1. And so I am removing the effects of the eigenvalue 1 from the matrix. If I remove the eigenvalue 1, I can also define this essential spectral radius, which is, let's define this. Suppose I take all of the eigenvalues in A, but I subtract the eigenvalue 1. And then I look at the largest maximum value of this, the maximum absolute value of these eigenvalues, and I call that the essential spectral radius. So intuitively, the picture is very easy. The picture is I have an eigenvalue at 1, right? I have an eigenvalue at 1, and I have other eigenvalues inside, right? And what I do is I remove the eigenvalue of 1 from consideration, and then I find the smallest disk that includes all of the other eigenvalues, and that is the essential spectral radius. Okay, perfect. Bottom line, I have defined delta k, a disagreement vector, which is xk minus its average, essentially. And then I define A deflated, maybe let me just write a symbol for it, to be A minus its rank 1 limit. Why is this useful? The reason it's useful, there's a couple of reasons. One is that you can rewrite in this new variable, so the system is xk plus 1 is equal to axk. But if you move to this shifted variable delta, the disagreement vector, subtracting the average from A, then you can show that the disagreement dynamics, so the dynamics of the disagreement vector, the state matrix, the state transition matrix, is just the deflated matrix A minus 1n W transpose. So subtracting the averages from the vector corresponds to deflating the matrix. And that's very useful because the next thing happens that when the matrix A is primitive, so we know it has a single, simple, strictly dominant eigenvalue, all the other eigenvalues strictly inside, the deflated matrix has the same eigenvalues and even eigenvectors of A, with one exception. The eigenvalue 1 is now substituted by the eigenvalue 0. Precisely, so if I go back to my picture, it's as if magically I took this eigenvalue of 1 and I have shifted it to 0. All the others are unchanged. And so now, because the matrix, if the matrix is primitive, if I now compute the row essential, this is the same as row of the deflated matrix, and now this is strictly less than 1. Now my deflated matrix has spectral radius strictly less than 1, equal to the essential spectral radius of the original matrix, but now my equation 5.8, my disagreement dynamics, is convergent. Is convergent because the spectral radius is less than 1, and so the limit of delta is 0, which once again means that X goes to consensus. This is not surprising in the least, and this is a confirmation of what we saw before. The only thing that I wanted to mention is that you can shift variable from X to delta, which is X minus W transpose X 1n. That corresponds to A shifting to its deflated version. And what happens is that delta goes to 0 asymptotically. It actually goes to 0. Let me make an extra comment. It's actually true that delta goes to 0 and the largest eigenvalue in magnitude of the matrix, of the deflated matrix, is this rho essential, So I will loosely say here, and I will give it more depth later on, goes to 0 with a rate, or with factor, I should say, because it's in discrete time, with contraction or a convergence factor rho essential of A. And the equation I wrote there is that actually it's true that delta K in 2 norm is upper bounded by rho essential of A to the power of K, which multiply delta at 0 with respect to 2. However, without further assumptions, it is not true that this convergence is monotonic. And two things happen. Well, first of all, you need to choose a delta, you need to choose a rho essential that it's a little bit larger than that, otherwise it's not true. And the other is that there is a number here greater than 1 that makes this equation come true. One can show this equation here. I'm not going to go over the proof right now, but the point is that the decrease of the norm of the disagreement vector is not monotonic in general when computed with respect to the 2 norm. Oops. Okay, so this is the comment that I have for you. I am interested in finding numbers, positive error quantities that converge to 0 monotonically. And if I take my first attempt here, taking the 2 norm of the disagreement vector, I made good progress. I did come up with such a notion, the error, the norm, the 2 norm of the disagreement vector, but it turns out that I fell a little short and that this is not monotonic decrease. So in other words, here I found no Lyapunov function in the language of control theory. I will skip the proof. It's relatively straightforward and it uses properties that you have already seen. Here is my second attempt in this section, and this is the attempt of using something called quadratic disagreement. But in this attempt, the key idea is that I will work with symmetric matrices. All right, so let's talk about this quadratic disagreement. It works like this. So I can look at this sum of square differences, and it's convenient to normalize it by 1 over n. I'm basically summing the pairwise differences between all I and j. And notice that in this sum, I am actually counting each pair ij twice, because I and j are both running from 1 to n. And it's very clear that this positive quantity, and non-negative, and it's equal to 0 if and only if x is a consensus vector, meaning to say every entry, every xi is equal to every other xj. So I'm going to call this the quadratic disagreement function. And before I continue, let me give you two interpretations of it. One is that, hey, I can write that as a quadratic form. So this is a quadratic form where you have a symmetric matrix pi sub n, and V quadratic disagreement, VQD, is just x transpose pi n x. And this pi n is a matrix that you can write out explicitly, and it looks one can show that this pi sub n is the orthogonal projection onto the vectors perpendicular to 1n. One can show that it's symmetric, and one can show that it is positive semi-definite. And then moreover, one can show that this VQD can be written simply as, again, the 2 norm of the disagreement vector. This time it is squared with the additional but now my disagreement vector is not using an arbitrary vector w, or well, the left dominant eigenvector w, it's using 1n. So here I'm writing x, I'm subtracting from x the average, let me just write average of all entry of x times 1n. And this is the same delta as before when w is equal to 1 over n 1n. All right. So this is, in some sense, this is the same quadratic cost function as in the previous slide. However, here I'm using w, a very specific w. It's the w that gives me the exact average. And remember, this is really corresponding intuitively to the case where A must be doubly stochastic. But here I will make the slightly stronger assumption that A is row stochastic and symmetric, which easily implies doubly stochastic. And I want to define one more quantity before I can get to the main theorem. And I will use this relatively unusual name to it. I will define something called the 2 coefficient of ergodicity. So there will also be another coefficient of ergodicity, which I'll call it 1. And the 2 coefficient of ergodicity, tau 2, is defined in this equation here with 2 equivalent formulas. It's either the induced norm of the deflated matrix, or it is the maximum value that a certain vector can take. And let me comment on both. So again, this matrix A minus 1n, 1 over n of 1n, 1n transpose, and there is a transpose here, forgive me, I forgot it there. This is the deflated matrix as before, with the assumption, again, that W is 1 over n, 1n. So it's the induced norm of the deflated matrix. And you should remember, what does induced norm mean? I haven't reviewed it in class. There was an exercise that I assigned, but the induced norm of a matrix, I hope you guys have all seen it in your matrix theory courses, is just the maximum 2 norm value, the maximum 2 norm of AX selected over all x's with 2 norm equal to 1. The other alternative expression for tau 2, it's basically saying, let me just rewrite it here, it's the maximum value that AY can take, where Y has norm 1. So this is looking very, very similar to the maximum induced norm, but the argument Y in this formula has to have the property of being perpendicular to 1n. So when I write y perpendicular to 1n, what I mean to say is that 1n transpose y is equal to 0. So this is rather similar to an induced norm, but not exactly. And so essentially, in this formula 5.13, the coefficient of ergodicity, it's either the induced norm of the deflated matrix. So I either subtract something from the matrix, I deflate the matrix, and then I take the induced norm, or I look at the possible maximum amplification of the matrix, which would be the induced norm, but as argument, I only use arguments that are perpendicular to 1n. So I hope you see that both definitions have something in common. They both, in some sense, get rid of the 1n, 1 eigenpair for the matrix A. All right. Why is this quadratic disagreement useful for the case of symmetric averaging algorithms? Well, symmetric averaging algorithm, which also means the graph is undirected, right? Well, the reason they're useful is because now I do get precisely what I wanted, which is a strict decrease. Well, let's work this out. Well, maybe let's start with condition 2. When the graph is connected, then tau 2 is equal to the same essential spectral radius we talked about earlier. And because the graph is connected, then the eigenvalues are strictly dominated. The eigenvalues which are not the Perron eigenvalue are all strictly dominated by the Perron eigenvalue 1. And so therefore the essential spectral radius is strictly less than 1. And moreover, okay, this I've discussed. And moreover, I now know, therefore, that this quantity here, this tau 2, is strictly less than 1. And so now this is saying that if I take the quadratic disagreement and I map it one time in one instant of time in the future, and I obtain the quadratic disagreement at ax, it has strictly decreased by a factor tau 2, the 2 coefficient of ergodicity. And so now consequence 3 in this theorem, in this lemma, is trivia. If you take multiple steps along the averaging algorithm, after k steps you have raised this number less than 1 to the power of k. Of course this is converging to 0 as exponentially fast, right? Monotonically and exponentially fast. So one of the key things is monotonically. So what we have discovered in a language that we will review in the nonlinear chapters, if I get to them in this course, or in any case that you may be familiar with if you've studied nonlinear systems theory, we have discovered that the quadratic disagreement function VQD is a quadratic Lyapunov function for my averaging algorithm, but that is true only when A is symmetric. That is true. Now, what do I have to prove in this lemma? 3 is an immediate consequence of 1 and 2. So I really just have to prove 1 and 2, but 1 and 2 are also very simple. I'm not going to spend time in the proof. I'll only tell you that the one key idea is to use the modal decomposition to compute that tau 2 coefficient of ergodicity, working with the norm of AY. That's all that's needed. And the first inequality is rather straightforward as well. It's just very simple manipulation. The first inequality, I mean to say, this condition 1. Condition 2, you use the expression of the 2 norm of AY and the modal decomposition of a symmetric matrix. Now I'm ready. What have I obtained so far? I have found the Lyapunov function, but only for the case where the matrix is symmetric. And before I leave this topic, I would like to give you a Lyapunov function that works also when the matrix is not symmetric, more generally. All right? And so this now is, what I'm showing to you right now, is going to be a genuinely different method of proof from the one based upon the Jordan normal form. So here, and also in the previous proof, by the way, even for the quadratic disagreement Lyapunov function when the averaging matrix is symmetric, even there I did not use the Jordan normal form, right? So now, here I'm going to find a monotonically decreasing function for you, and we will, which is going to be easy to use also for the case of time varying and nonlinear dynamical systems. So here's the way it works. I'm going to define a new disagreement function. Remember, the language is disagreement vector is delta and it has n entries. When I say disagreement function or quadratic disagreement or min-max disagreement, I mean to say a scalar. Here I take the vector x and I subtract from the largest entry in x the smallest entry in x. And I will call this the max-min disagreement function. Really I should say max minus mean, but it's just too long, so I'm just going to say max-min disagreement. And this function has the same property as the quadratic disagreement function, which is to say that it's clearly non-negative and it's equal to 0 if and only if x is a consensus vector, which means that it is a scalar multiple of the vector 1n. For this candidate Lyapunov function, so I have a function I'm going to hope to show that is decreasing, but I need to find for you what is the rate with respect to which this function is decreasing. What is that rate? How do I get it? Well, this is the notion of the ergodicity coefficient that I'm about to introduce. And here I need to define the one coefficient of ergodicity. And if you look at this formula, the first row, this is exactly as before with one notable difference. So tau 1 of A, it's the maximum value achieved by AY when the norm of y is 1 and y is perpendicular to 1n. So this will be the definition from before. and before I had used the 2 norm. Here there are two differences. Sorry, I said one, but it's 2. There are 2 differences. The first difference is that I need to use the 1 norm. So I have 1 norm here and 1 norm there. And let me remind you, the 1 norm of a vector y is very simple to understand. It is the sum of the absolute value of yi, where I runs from 1 through n. So it's the sum of the absolute value of the entries of y. That's the 1 norm. And the other difference, that it's not a real difference, because before we were dealing with a symmetric matrix. Here instead A will not be symmetric in general. It's an asymmetric row stochastic matrix, very general, but then I need to remember to put a transpose sign right there. Okay, so this is the tau 1 coefficient of ergodicity requires the transpose in there. So it's for the transpose matrix. So this is my definition of tau 1. And before I proceed, let me make a comment that some careful algebra, not sophisticated, ultimately every step is really elementary. However, one really needs to sit down carefully and do it very carefully, step by step, will show that any one of these 3 expressions is equivalent. I have 3 expressions. This is 1 here with this kind of a almost like an induced norm, 2 and 3. There are 3 expressions for tau 1. They're equivalent. The proof that they're equivalent is tedious but not particularly sophisticated and requires a fair amount of time. I will skip it in the interest of brevity. I will just say that there is an expression, there is a way of verifying that this holds, and it's well known, and there's also an absolutely beautiful history behind this tau 1 coefficient and these equivalences between these quantities, the history going all the way back to a 1906 paper by a Russian scientist by the name of Alexei Markov, who was the first to study row stochastic matrices in the context of something now referred to as Markov processes. But for us, for today, they're just equal. And now comes my theorem or my lemma about Lyapunov functions. And this lemma is very similar to the one before. Let me tell you the similarity there. So no matter where you are, you have this one-step decrease. So if I map x into ax, I have a coefficient tau 1 that tells me how does Vmax vary. Well, it's an upper bound. And under some conditions, which I will review in a second, this coefficient will be less than 1. And therefore, if I take multiple steps k, I will come to explain this, but essentially this is the same rate of exponential or convergence to 0 as before. Tau 1 dictates that rate. This has the potential to work for any matrix A that is also not symmetric. There is, however, also one complication, unfortunately. The theory is great, but there is one slight complication. So, remember, I said to you that A is indecomposable when there exists a k such that a to the k has a strictly positive column j, strictly positive. So you can, a node is globally reachable by all other nodes. Now, here, the condition is that tau 1 of A is strictly less than 1 if and only if A is scrambling, which is another property we haven't discussed. Scrambling means that any 2 nodes have a common out neighbor. So in other words, A is scrambling if you take any 2 nodes, I and j, you look at this I and you look at the j, there exists at least one node. I apologize, let's change notation. Let's call it I1 and I2. There exists at least one node j such that these are both positive numbers. So I and j both jump I1 and I2 both jump to J in one step. And you can find one such J for every pair. It turns out that if the matrix A is indecomposable, no, let me say it the other way. If a matrix A is scrambling, then it is clear that it must also be indecomposable, because as you keep taking more and more steps, you will reach to the point where the column is positive. Once the column is positive, right? So if A is indecomposable, what I'm trying to say is that if A is decomposable, A to the K is scrambling, right? A to the K is scrambling because at the time when the same column works for everybody, then of course the matrix has reached, the property of being scrambling. So what that means is the following. That means is that, and let me remind you that there exists an index H such that A, we've already seen this, so this is just a reminder essentially. So I can find a power H such that AH is strictly positive if and only if G contains the global reachable node and the subgraph of global reachable nodes is aperiodic. So that's one thing. And therefore, if I'm in this property that I have a global reachable node and the subgraph is aperiodic, then I know that A to the H is scrambling, which means that tau 1 A to the H is less than 1, and then I can take multiple powers, and that will be going to 0 exponentially fast. Okay, so to cut a long story short here, what I've achieved is I've shown to you that there is a Lyapunov function, and this Lyapunov function is the function Vmax minus Vmin. And the coefficient with respect to which the function is decreasing is tau 1 of A, but you need to wait, sorry, this has been written badly, let me write it better. So it's tau 1 of A after some number of steps. And now that would be finally be less than 1. All right, this is the conclusion of my discussion. The proof, I have included it here. Really the key step is showing this very first inequality, and it is a very elegant little proof. Again, it doesn't use anything sophisticated, but just careful bookkeeping, and it's very smart in the way that it is set up. I will now take a little break. Excellent. So I'm now ready to talk to you a little bit about my two appendices in this chapter, and they have to do with a design problem and an analysis problem. So the question that is at hand here, how do I design weights on my graphs? So, and this is very similar to something we did in chapter 1 as an example. Imagine you're given a graph, and a graph is a binary object, and you need to define a row stochastic matrix. You want to be computing averages. How do you do that? So here is, in this appendix, in this supplementary information, essentially, there are two strategies. They're very simple. I invite you to read them. I'm not going to discuss them in great detail. I will only say that there is a strategy called the equal neighbor strategy. And so if you are node 2, your neighbors are 1, 3, and 4. And so you could design an averaging algorithm where the coefficients are 1/3, 1/3, 1/3, and you give 0 weight to yourself. The same algorithm you apply to everybody. For example, the first node you get a 1. This is called the equal neighbor model, and you can write an appropriate formula for the way in which the matrices come together. For the equal neighbor model, there is one remarkable property, and that is that it is not the matrix, the resulting row stochastic matrix is not doubly stochastic, so the left dominant eigenvector is not a vector of 1s, but it is a vector that can be computed, and it has to do precisely with the degrees of the node. It's essentially true that the W vector is the vector of degrees normalized to sum up to 1. So that's the key property. The second observation, and let me just keep the proof. The second observation, in chapter 1, we use the equal neighbor model. However, before using it, we summed self loops. So we took a graph that was undirected, and the first thing we did was we essentially added self loops, and then we applied the equal neighbor model. So we went from A, we went to A plus identity of dimension 4, and then to this matrix we apply the equal neighbor model. So that's all there is to it. And then this is the same matrix AWSN that we have already seen. Now what that means is that my W vector for the WSN matrix is equal to what? The vector of out degrees plus 1, because I've added self loop. So notice this is node 1, so there's one node going to 2 and a self node. So that number is 2. For node 2, I have the value 4, and for node 3 and 4, the number of the degree is 3 and 3. Now you take the, oops, forgive me. Now you take this vector and you normalize it to sum to 1. So the sum of that vector is 12, so you need to divide by 1/12. And if you divide by 1/12, you get exactly 1/6, 1/3, 1/4, 1/4, which is the vector that we have already seen. So just to close the check. So just to confirm everything. So in this appendix, first we discussed the equal neighbor model, and it's a beautiful model, it has properties, but it does not give you a doubly stochastic matrix. What if I really wanted a doubly stochastic matrix? Here's an algorithm that does that. It's called the Metropolis-Hastings algorithm. It's a very important algorithm in optimization. It's used quite a bit. The idea is the following. I will try to design a matrix that is symmetric. Symmetric. How do I do that? I assign weights on the edges that are the same weight going from left to right or right to left. Now, if you assign a weight equal to 0.5 to the edges of node 2, what happens? Imagine I were to apply 0.5 here, 0.5 there, 0.5 here. Now 3 times 0.5 is equal to 1.5. Too much. You cannot construct a stochastic matrix applying 0.5 to those edges. So in other words, if your attempt is that of giving equal weight to for any 2 nodes there is an edge, I want to give the same weight. I just need to be careful that that weight is not too large. And what happens is that once I select an appropriate weight, for example here in this particular example 1/4 is a good idea. Then what happens? I assign to myself node 2 the remainder weight. So that is 1 minus 1/4 plus 1/4 plus 1/4, because I assign 1/4 to my 3 outgoing edges. So that means that node 2 assigns to itself 1/4. Node 1 has only one edge, therefore node 1 assigns to itself a different value, 3/4. Perfect. So the Metropolis-Hastings algorithm is an algorithm that tells you if you have an edge from between I and j, look at the degree of I and j, look at the largest of that degree, sum a 1, and use 1 over that as your weight. When you do that, you're guaranteed that that number is not too large. After you do that, you can set the self weights as 1 minus the sum of that, and if you have no edge, you set 0. If you use this algorithm, you obtain a matrix for the same graph, for the same topology, which has, relatively unusual weights on the diagonal. They're perhaps hard to predict, but it is symmetric. And so if it is symmetric, that means that it is doubly stochastic. So if your design purpose was that of achieving average consensus, the Metropolis-Hastings model achieves that. This is precisely one of the questions that we had in chapter 1. We said something like, suppose I use this model, which was the equal neighbor model, does it achieve average consensus? Now we know the answer is no, and we also know the design answer, which is use Metropolis-Hastings instead of using equal neighbor. The last appendix of this chapter has to do with something called centrality scores. It's a beautiful subject studied in network science, not so much in the dynamics of network systems. But basically the intuition is, and I have a table, let me get to the table here. The intuition is that there are many different ways of taking a graph, even a weighted directed graph, and trying to determine which nodes are important, which nodes are not important. And the word centrality is precisely a synonym for importance. And what we've seen in this class is eigenvector centrality, which arises in our averaging problems. But there are many other notions of centrality. Even just a degree could serve as a centrality notion, page rank centrality, Katz's closeness, and betweenness centrality. And so I invite you to read about this either in my section 5.5 or even on Wikipedia would be just about the same. And here's just a picture that takes the same graph, is due to Dr. Brandes, same graph, undirected, unweighted, and shows that if you use different notions of centrality, the node that ends up having the largest centrality is node 2, 3, 8, 9, sorry, there's some numbering here. It changes, right? So these are different notions of centrality. So when you are tackled with the problem and you need to define which nodes are most important, then you need to be careful. You can use one of those notions, but you are going to get an answer that very much depends upon which technique you have adopted. In conclusion, we have seen, in some detail, we have seen how to go from the content of chapter 2, 3, and 4 and fully answer the questions stated in chapter 1, giving necessary and sufficient conditions for consensus, giving necessary and sufficient conditions for average consensus, understanding also that in some cases you may get asymptotic disagreement or dissensus, so not always does a group reach you, even for the very simple linear averaging model I've described. And then we've done all of that using the matrix power theorem, which is proved using Jordan normal form. And then we have also made an effort to design Lyapunov functions, the quadratic and the min-max disagreement functions, and shown that they have contraction coefficients that are referred to as ergodicity coefficients, and they can be less than 1 under reasonable assumptions. I've then also shown to you two simple design algorithms, equal neighbor and metropolis hastings, and given you a little bit of insight for these notions of centrality. With that, I wish to thank you all very much and see you for the next lecture.